dynamics written as R times Y. This is an LTI, right? Where R is what? Is the logarithm of C, okay? Okay? By the way, here we can also call V, look at this. The flow along the time varying vector field phi, we called it the exponential, right? This is an exponential representation of F. So, and this is also an exponential representation of V. So we're looking for V whose exponential matches the exponential of this guy. What do? You take the logarithm, right? So indeed, V in this definition, you can say V is the logarithm of the chronological exponential. Right? Just a notation in the back of our mind, but it doesn't add much. Okay, so anyway, this is the Fluke. Averaging is very different. Averaging is very different. So the very first step, it's like, here we want to have it on the canonical form. The same here, please put it in a canonical form. The canonical form is x dot is epsilon f of t, x and epsilon. This is one averaging. And then just apply averaging, please. When we apply averaging, what do we get? We get the average dynamic, x bar dot x epsilon, f bar of x bar. And this f bar is nothing but the average of f over the period. Okay? So this is 1 bar, the average dynamics. What is the relation? The relation that we know is that the x of t versus x bar, they are close to each other, or the rest. And if the average of dynamics is stable, exponentially stable, this guy is also exponentially stable for small enough epsilon. This is the issue, for small enough epsilon. So let's see. Please look at this here. The main concept behind averaging is what? To replace your time-varying differential equation by time-invariant differential equation, whose stability characteristics help you to infer stability characteristics of the time variant, right? So averaging help you do that, but unfortunately it's approximate, because the relation between the time-varying dynamics and the time-average dynamics is approximate for small enough epsilon. What does Fluke do? If you look at Fluke, well, people always stop Fluke here. We don't really, when we practice Fluke, we just come here, we simulate for time 1 period, get the monodromy, get the eigenvalues, they should be within the unit circle, we're done. We never go here. But we have this result at our disposal. What's this result? Look at this. This is a time average system. And you typically, Fluke, it's very rarely to be found in books that Fluke is written as an exact averaging. Look at this. This is a time-invariant system corresponding to the time-varying one, whose stability characteristics help you to infer stability characteristics of the time-varying one. This is nothing but averaging. And it's actually exact averaging, because the relation between the average dynamics y and the time periodic dynamics z is exact, is not approximate, doesn't depend on the smallness or largeness of any parameter. It's exact always for any time. If this guy is exponentially stable, that guy is exponentially stable always. Here, this statement is not always, it's for small enough epsilon. We don't know how small epsilon should be. Okay? So Fluke is indeed, can be seen as exact averaging. So this equation, 1 LTI, is actually complete or exact averaging of the 1 LTP, right? So for linear version, we can get exact averaging or complete averaging, no approximation. Okay? Any questions so far? So what Sarichev and Vela did, Sarichev 2000 and Vela dissertation 2003, they did the same for nonlinear case. Let's do this hierarchy exactly the same. What is the time average, what's the time invariant system with stability characteristics can help you to exactly infer stability characteristics of the time varying system? Well, what was the unique aspect of this one LTI that made it possible? The unique aspect was, if you remember, that the flow along this R, right, from here, the flow along R for time t, this vector field Ry, matches the flow along A of tz for the same time. Remember this point? I told you to review the flow of these two systems, time periodic and time invariant, they match every time period. So if you want to extend this to the nonlinear case, please find the system, a time invariant system, whose flow for one period matches the flow of the time varying system for one period. So we are looking, we're going to define now, the average of dynamics, or averaging, complete averaging. The word complete averaging is due to Sarichev. Complete averaging of the equation 1, the nonlinear time period. Okay? By this vector field f bar, the average of it, complete averaging of it. So f bar must satisfy the following: the flow along f bar, its time invariant for one period, should match the flow along the exact dynamics for one period. Right? Any question about that? Okay, we know from chronological calculus that we can find, there may exist a V, it doesn't always exist, okay? But we can try to find a V T whose flow for unit time, right, matches the flow of this guy at that time, right? So if you want to just make this as, if you want to have this for also the same time, that's super easy. I will have the time here t and divide here by t of my vector field because it's time invariant, right? So from this, their complete averaging is nothing but this guy. Okay? So my complete averaging is 1 over t. Remember the Vt, it was an infinite series. This was the first term, integral of f, right? The second term was an iterated integral f. I'm sorry, it wasn't. It was an E bracket, right? Yes. So here 0 tau 1, we had an E bracket. We have 1 over half Lie bracket f tau 2 f tau 1 d tau 1 d tau 2, or the other way around. Yeah, right? So you get the exact averaging is an infinite series. So you can actually write down, we can write down f bar as an infinite series from k equal 1 to infinity as lambda k divided by k factorial. Okay? So this is the exact averaging or complete averaging. This infinite series, if it's exponentially stable, if you manage to get the infinite series, if it's exponentially stable, then the time periodic system is exponentially stable irrespective of epsilon. There is no approximation. It's exact averaging, right? One more thing.
Has to be exponential. How does it go?
That's a good question. So I'm tempted to say yes, it works for asymptotically stable, but I'm not sure. I'm not sure. Okay. So one thing here, if we have epsilons in front of our f's, if you want to put it, there is no forcing here to put it in the canonical form of averaging, which is a great plus. Although, please put it in the canonical form of averaging. This thing works whatsoever, right? But when we put it in the canonical form of averaging, so we have epsilon here, epsilon in front of everything, so epsilon here, epsilon here, epsilon here. Please put epsilon in front of everything. So here is epsilon, epsilon, you get epsilon squared, right? And so, so we have here epsilon to the k. So here is why it's more, you know, if we truncate, we'll get better results. If epsilon is small, actually I'll show you what is the first lambda. Obviously here is the first lambda. So lambda 1 is just the average of f. This is the first order averaging, right? What is lambda 2? Well, here is lambda 2. So take the 2, take the epsilon squared. So it's just the average of the Lie bracket of the integral of f, say tau x d tau, and f of t of x dt. And lambda 3, they are all defined by f's and the Lie brackets between f and its integrals. You can complete it analytically.